Every day we feel forces. We push things, and things push us. Forces hold things together and keep them apart. It's no surprise, then, that the study of forces is very important to understanding the physical interactions that shape our universe. The foundations to this study were codified by Isaac Newton in his laws of motion. Today we will be primarily utilizing his second law of motion, perhaps the second most well-known equation in all of physics. The sum of the forces equals mass times acceleration. The first symbol is the uppercase Greek letter sigma, which is used to denote a sum. Sigma F is shorthand for adding up all of the forces, sometimes equivalently written as the net force. The arrows on F and A denote that they are vectors. Sometimes this is represented with bold letters instead. They are vectors because we can recognize that they have a direction. If we push with a force in one direction, an object will accelerate in that direction. If we push in the opposite direction, it moves in the opposite direction. If two equal forces act on an object in the same direction, they combine into a stronger force. In opposite directions, they cancel out, and the object doesn't move. If the forces are at some other angle to each other, then we'll get a result somewhere in between. We can conclude that it's not enough to simply add the strength of the forces. We must add them as vectors to account for their directions. To review adding vectors, watch our video on vector addition. Let's try applying the equation of Newton's second law. Imagine the simplest example, a block floating in empty space. There are no forces on the object, so the sum of the forces is 0. Therefore, the acceleration must be 0. Another case, a block in freefall with no air resistance. The only force on the block is gravity, so the net force is simply F sub g downward. This equals its mass times acceleration, as per Newton's second law. We know that an object in freefall accelerates at g, 9.81 meters per second squared. Therefore, the force of gravity equals mg. G is the acceleration. Even when an object near Earth isn't in freefall, it will still have this gravitational force, mg. So how do we set up Newton's second law when we have more complicated situations? This is where one of our most useful tools comes in, the free body diagram. The free body diagram, or FBD, is simply a drawing that shows all of the forces acting on an object. Learning to make good and accurate FBDs is extremely helpful for properly setting up and solving Newton's second law. Let's take the simple example of a block resting on the ground. What are the forces acting on the block? Gravity is pulling the block downward with a force equal to mg, its weight. The ground pushes up with a force which we call the normal force. Why is this force here? Consider this. The sum of the forces must be equal to mass times acceleration. The block isn't accelerating, so A equals 0. This means that the sum of the forces equals 0. So, there must be this normal force, which is equal and opposite to the gravitational force. The normal force can be thought of as the reason why things don't just fall apart when you push on them. Things have structural integrity which pushes back on you when you push on it. One more example where we now use 2 dimensions, a block being pulled across the ground by a rope without friction. Because we have forces moving in different directions, we must make sure to consider that the forces are adding as vectors. A common way to do this is to split Newton's second law into 2 equations, one for the x dimension and one for the y dimension. This lets us look at the x and y forces to get x and y accelerations separately. In the y dimension, we have the same situation as the last example. The y forces are gravity downward, mg, and the normal force upward. These must cancel out because the block doesn't move up or down. So, the sum of the y forces is 0, and therefore the y acceleration is 0. In the x dimension, there is only the force of the rope tension, T. So, the x equation of Newton's second law gives us T equals m times a sub x. Thus, the x acceleration equals the tension divided by the block's mass. Because there's no y acceleration, the total acceleration of the block is t divided by m toward the right. The situations we looked at here were simple, but they are foundational to the understanding of more complicated systems. In the upcoming videos of this chapter, we will investigate new methods of applying our process, as well as how to deal with friction and other forces.